Okay, finding limits, if they exist. So we need to find the limit if it exists. On question 1, a majority of the time these limits can be found using direct substitution. So you plug in a 1 into the expression for all the x's. So this would be 1 plus 3 over 6 times 1, which is 6 plus 1. So it would be 4/7. Now the problem here is if we use direct substitution, we'd have 0 squared plus 1 over 0. Can't divide by 0. So this limit doesn't exist. Now, question 3, if we tried direct substitution right at the beginning, we would have negative 2 squared plus 4 minus 4 is 0. So it appears we have the same situation as on question 2. But question 3 is a situation where you can factor the denominator, and you have common factors on the top and bottom, so we have 1 over x minus 2. Now we can take the limit as x approaches negative 2. If you plug in a negative 2 for x, you get negative 2 minus 2, which is negative 4, so it's negative 1/4. And the reason we had to say on number 2 it doesn't exist is we were not able to factor anything out and simplify. So on question 4, describe the intervals in which the function is continuous. A lot of times a function is continuous on the entire real number line from negative infinity to infinity. If there are discontinuities in a function, first you have to find out where those discontinuities are, and then identify the appropriate intervals. So on question 4, x plus 2 over x cannot equal 0. So if we were to graph this function, there would be no x values of 0 on the function. That's a discontinuity. It happens to be a vertical asymptote. So we would say there's a discontinuity at x equals 0. And then the second part of the question says, identify the conditions of continuity that are not satisfied. Well, in order for a function to be continuous at a particular x value, the conditions for continuity are, let me do this over here, so at any particular x value, like x equals c, f of c has to be defined. The limit as x approaches c has to exist, and the limit has to equal f of c. These are the 3 conditions for continuity at a particular x value. So the ones that are not satisfied for this problem is f of 0 is not defined, and the limit as x approaches 0 of f of x doesn't exist. Alright, question 5 here. We need to find the derivative using the limit definition. It's very particular. We could find the derivative of this pretty easily using basic properties of differentiation, but it says use the limit definition. So the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So we're going to have a delta x on the bottom, and we're subtracting the function over here, and then this side of the numerator is f of x plus delta x, so instead of x squared, that's x plus delta x squared plus 10. Then we have to simplify that. So we're subtracting x squared minus 10 over here. And then x plus delta x squared is x squared plus 2x delta x plus delta x squared. And then I need to have room for that plus 10. So minus x squared minus 10. So a lot of things cancel here. Plus 10, minus x squared, positive x squared. So we have the limit as delta x approaches 0 of 2x delta x plus delta x squared over delta x. Now this delta x on the bottom can cancel with that delta x and one of these delta x's. So this turns into the limit as delta x approaches 0 of 2x plus delta x. Now this can be evaluated by direct substitution. The reason that we had to simplify so much is every single one of these prior limits would give us a 0 on the denominator, here and here. We no longer have a denominator, and if we plugged in a 0 for this delta x, that just goes to 0. So the derivative is 2x. Now the point of the problem was not just to find the derivative, but we want to find the slope of the tangent line at this given point. And that's what the derivative is for. It's to help you find the slope of a tangent line at a particular point. So at 2, 14, the slope using this function here, 2x, is 2 times our x value, which is 2. So that's equal to 4. Now the equation of the tangent line needs to be y equals mx plus b. 4 is the slope, okay, and this we have x and y right here. We have x equals 2, y equals 14. So we plug in 14, 4 times 2 plus b. 4 times 2 is 8, 14 minus 8 is 6. So 6 is equal to b, so the equation is y equals 4x plus 6. So in 2.2 we learned a much quicker and easier way of finding derivatives than using the limit definition. So for question 6, if f of x is equal to 2x to the 5th over 7, we need to find f prime. F prime, remember, is the derivative. So one of the rules is the constant multiplier, the 2 and the 7. So 2x to the 5th over 7 could be thought of as 2/7 multiplied by x to the 5th. And rather than taking the derivative of the entire expression like this, the constant multiple rule says that's the same as taking out the 2/7 and then just taking the derivative of x to the 5th. The derivative of x to the 5th is 5, and then you decrease the power by 1. 5 times 2/7 is 10/7. So the answer is 10/7 times x to the 4. Question 7. The property or rule to apply here is instead of taking the derivative of the entire expression, you could take the derivative of each individual piece. So it'll be the derivative of 2x to the 4 minus the derivative of 3x squared plus the derivative of x. So here we're going to get 8x to the 3rd. Here we're going to get minus 6x. The derivative of x is just 1. And again, like I said in class, these are just samples of what you learned back in 2.2. This doesn't mean that this is all you can expect on a test. This is just a sampling. You really ought to go through 2.2's homework and the section and then look at some other sample problem. Make sure you understand the idea in section 2.2, which is rules of differentiation. 2.3, a rate of change. That's another way of using a derivative is to describe a rate of change, because a derivative tells you the slope of a tangent line, and a slope is a rate of change. So, a ball is thrown from a 300-foot building, initial velocity of 24 feet per second. So, the average velocity in this case of the ball over the interval from 1 to 2 is going to use the formula f of x2 minus f of x1 all over x2 minus x1, where this would be x1 and that's x2. So it would be f of 2 minus f of 1 all over 2 minus 1. Now, what we need to have is a function that describes the motion of this ball. So we learned that the position function of a falling object, s of t, is negative 16t squared plus the initial velocity of t plus the initial height. So in our case, s of t is going to equal negative 16t squared. And it's thrown upwards, so it's a positive velocity, so plus 24t plus 300. Now s is just a common letter used for position. We're using f here, so they're the same thing. So it's going to be s of 2 minus s of 1 all over 1 essentially. So s of 2, if you were to plug in a 2 into the function, s of 2 turns out to be 284, s of 1 turns out to be 308. So you get negative 24 feet per second. Now the instantaneous velocity is different than the average velocity. The instantaneous velocity, we need to have the velocity function. The velocity function, v of t, is equal to the derivative of the position function, which is negative 32t plus 24. If we take this position function here or here and take the derivative of it, so at time t equals 2, this is going to be negative 32 times 2 plus 24, which is negative 40 feet per second. How long will it take for the ball to hit the ground? Well, how long will it take? This means we're going to be finding a time value, so we're going to be solving for t. And when the ball hits the ground, its height is 0. So we're going to use the position function s of t and set it equal to 0, because we want to find out when the height is equal to 0. So 0 equals negative 16t squared plus 24t plus 300. Okay. Now you can factor out a negative 4. Minus 6t and 75. And then if you divide by negative 4, you have 0 equals 4t squared minus 6t minus 75. Now, I know in the examples and in some of the homework problems, this could be solved by factoring. Unfortunately, this doesn't factor, so you have to use the quadratic formula. So if you use the quadratic formula, you would end up with 6 plus or minus the square root of 1,236 all over 8. Now you got to stop for a moment and think here. T represents time. And here we have 6 plus the square root and 6 minus the square root. The square root of 1,236 is much bigger than 6, and if we're subtracting that from 6, we're going to get a negative value for time. That doesn't make sense, so it wouldn't be correct to have plus or minus. We're going to have 6 plus the square root of 1,236 all over 8 as our value of time. And since we don't have a calculator, that's just going to be how we leave it. The velocity of the ball when it hits the ground, well, first of all, when does it hit the ground? And it hits the ground at that time value. So this is another instantaneous velocity problem. We need to find the instantaneous velocity at this time value. So the velocity, remember, was equal to negative 32t plus 24. So it's negative 32 times 6 plus the square root of 1,236 all over 8 plus 24. And then using some simplifying here, we would end up with negative 24 minus 4 square roots of 1,236 plus 24. Those would cancel. So it's negative 4 square roots of 1,236 feet per second. Now it may turn out that this simplifies here, the square root of 1,236. I'm not super concerned about this simplifying. But just to be exact, if we divided that by 2, or by 4 rather, it's 4 times 309. So the 4 is going to move out as a 2. So we'd make negative 8 times the square root of 309 feet per second. And it should be a negative velocity because it's traveling towards the ground. Okay, question 9. So find the additional profit when sales increase from 10 to 11. So we need to take the profit function and find out what the profit was at 10 units and find out what the profit was at 11 units and find the difference. So the profit at 10 units, if we just plugged in a 10 to the function, turns out to be $50. And the profit at 11 units turns out to be $59.50. So the profit increases by $9.50. So what part B is meant to do is illustrate that using marginals you can estimate the rate of change, and it's going to be pretty close to the actual change. So marginal profit is dP over dx. So if you take the derivative of the profit function, so I'm going to rewrite this as negative 1/2 times x squared plus 20x minus 100. If the 2 drops down, multiplies with 1/2, it's going to cancel out, so it's negative x. The derivative of 20x is just 20. The derivative of negative 100 is 0. So the derivative here is negative x plus 20. And at x equals 10, the marginal dP over dx is equal to 10. And since it's a rate of change, it's $10 per unit. So what this is describing is it would increase $10 per unit if we increase production or sales. And that's pretty accurate because when sales increase from 10 to 11 units, that's an increase of 1 unit. the actual increase in profit was $9.50, and this is saying that it's about $10 per unit. Alright, in 2.3 through 2.5 we learned some more rules and properties of differentiation. This one here, for example, number 10 would be the product rule. So if taking the derivative of the product of two functions, it would be f prime of g, or f prime times g plus f times g prime. So y prime would be the derivative of the f function, which is 6x multiplied by the g function, x squared minus 2x, and we add the f function multiplied by the derivative of the g function, okay, and then simplify. Actually, I got this part wrong. Now I'm looking at it. The derivative of the g function is 2x minus 2. Yeah. Sorry about that. So here we'd have to distribute this together, and we get 6x cubed minus 6x squared plus 14x minus 14. Combine your like terms, and we get 12x cubed minus 18x squared plus 14x minus 14. Question 11 is meant to be an illustration of the quotient rule. So we have an h function here and a g function. So the phrase is low d high minus high d low all over low squared. So it would be low d high minus high d low all over low squared in this case. So f prime of x would be the low function, 3x plus 1, multiplied by the derivative of the high function, so that's negative 5, minus the high function, h, times the derivative of the low function, all over the low function squared, so that's 3x plus 1 squared. Let me simplify. So this is negative 15x minus 5 minus 6 plus 15x. So the 15x's would cancel, and negative 5 minus 6 is negative 11. And you can multiply this out if you want, or you can just leave it as 3x plus 1 squared. I'm not too concerned about that there on the bottom. Question 12 is meant to be an illustration of the chain rule, because we have an instance of g of h of x, where we have a function inside of a function. H of x would be like the 5x squared plus 2 function, and the g function would be cubing it. So we really have an instance of two functions here. So the derivative of a composition is equal to g prime times h prime, essentially. So we have to take the derivative of the outer function, which would just be dropping down the 3 in front and increasing the power by 1. So this would be 3 times 5x squared plus 2 to the second power. That's the derivative of the outer function. Now we multiply that by the derivative of the inner function, which is 10x. Okay. I'm going to simplify a little bit here. finally we get 750 x to the fifth plus 600 x to the third plus 120 x.